Hi, I'm Dave Perellis, an engineer at Tektronix. In this next video in our XYZ series, I'm going to show you how to use a few more automated scope measurements, specifically mean, RMS, and area measurements. They'll come in really handy for characterizing analog and power waveforms. I'm going to use a TBS2000 scope and an arbitrary function generator, but what you'll learn should apply to any digital scope that supports these measurements. In the last video, we showed how to perform basic amplitude measurements like peak-to-peak, maximum, and minimum. In this video, you'll learn how to make a few more important measurements related to amplitude, and you just might get some insight into some of the math behind them. I'm going to start with the mean measurement, but before I show you how to make the measurement, let's take a look at how this measurement works. The math the scope does to measure the mean value of the waveform is pretty straightforward. The mean value, or average, is computed by summing the value of each point and dividing by the number of points. If a signal is as negative as it is positive, that is, if it's symmetrical around 0, the mean value will be 0. If it's more positive, then the average will be positive, and vice versa. So the mean value can be used to evaluate the symmetry of a waveform and check for any DC offset. Let's take a look at how this works on a scope. I'm going to select the measurements from the measurement menu. First, let's check the gating. Gating determines which sample points are used to calculate the measurement. For this example, we'll use screen gating. This will use the sample points on the screen to calculate the measurements. Now I'll turn on the mean measurement. I'll also turn on cycle mean. Measurements that begin with the word cycle are calculated over the first full cycle in the gated part of the record. In this case, that's the screen. I'll also turn on min and max for reference. And I'll turn off peak to peak because we don't need it. The min and max are about equal but opposite. And this sine wave is vertically symmetrical around 0 volts. In other words, there's no DC offset. The cycle mean is pretty close to 0 volts. But the mean is negative. Why is that? Remember, the mean measurement is looking at all the points on the screen. We have about 3.5 positive cycles, but we have about 3 and say 3/4 negative cycles. So the mean is negative because we have more negative cycles than positive cycles. The cycle mean measurement automatically finds the first cycle of the sine wave and performs the measurement over just that cycle. For a periodic signal like this one, cycle mean is a better choice. For non-periodic signals, you can use cursor gating to determine exactly which points are used in the measurement. I'm going to add 0.5 volt of DC offset on the function generator. Now the measurements of max and min have different absolute values. When the input signal has a DC offset, you can use the mean measurement to measure the size of the offset. Here it's about 500 millivolts, which is exactly what I dialed in. So the mean value measurement comes in handy when you're quantifying offset. But if we want to understand the energy in a symmetrical waveform centered around 0 volts, like this, the fact that the mean is 0 volts doesn't tell us anything about the amount of energy. Root mean square, or RMS, is another statistical measure of a signal. You can think of RMS as a kind of mathematical AC to DC converter. For an AC waveform, RMS gives an equivalent DC value that would generate the same heat or deliver the same amount of power. Power is proportional to the square of voltage or current. So when it comes to power, the polarity of the waveform doesn't matter. Negative voltages or current can do just as much work as positive voltages or current. And since an RMS measurement relates to power, it starts by squaring every point in the waveform. Then it takes an average and a square root. An RMS value is always positive. Let's have a look at the sine wave on the scope again. I'm going to turn on cycle RMS and RMS. I'll turn off the mean measurement. We don't need that one anymore. There are a few things to notice. Even though the cycle mean is still around 0 volts, the cycle RMS is a little over 700 millivolts, or about 70% of the peak. So the amplitude or max is 1 volt. And for a pure sine wave with no offset, the RMS value is always going to be around 70 or 71% of the peak. For a triangle wave, the RMS value will be around 58% of the peak. And if we look at a square wave cycle RMS or RMS will be about the same as the peak voltage. I'll switch back to sine on my function generator. And as I mentioned earlier, the RMS value is independent of signal polarity. Let's prove it to ourselves by feeding a rectified version of this sine wave into the scope. Even after full wave rectifying the sine wave, the RMS value stays at 71% of the max. Area measurements determine the area between the waveform and 0. It's computed by integrating the waveform over time. Areas can be positive or negative. Areas above 0 are positive and areas below 0 are negative. Area is useful for finding values that are integral functions of voltage, current, or power. For example, an area measurement on a current waveform represents the amount of charge delivered over time. Area measurement is also used with power waveforms to compute the energy delivered or consumed over time. In this setup, I have a 0.33 microfarad capacitor hooked up in series with a 100 ohm resistor. I have a probe hooked up across the resistor, making sure that I've got the ground of the probe tied to the ground of the generator. Thanks to Ohm's law, the resistor can convert the current flowing in the capacitor into a voltage. I've set the scope up to scale the voltage into amps. I'm driving the circuit with a positive pulse. And you can see the charging current when the pulse goes high, and you can see the discharge when the pulse goes back to 0. Now we can use the area measurement to integrate the current and determine how much charge is stored in the capacitor. Let's focus on the charging part of the cycle. Since I want to focus specifically on the charging part of the cycle, I'm going to use cursor gating. There, now I can specify exactly the part of the waveform I want to use. And I'll go in and turn on the area measurement. I'll also turn on the max measurement just for reference. As you might remember from physics class, the charge stored on a capacitor is simply capacitance times voltage. So we would expect the charge to be about 0.33 microfarads times 1 volt, which equals 330 nanocoulombs. The area measurement integrates the area underneath the curve, and it shows about 330 nanoamp seconds. which is equivalent to about 330 nanocoulombs. So thankfully, the laws of physics have been proven once again. In this video, I've shown you how to use automated mean, RMS, and area measurements to characterize analog and power waveforms. In the next video, we'll focus on digital signals and pulses. Thanks for watching.
Find out more at Vicom's website.